Hello and welcome back. In this video I'll talk about material derivatives because I just found out about them and I thought they were really cool. So let's dive right in. There are many symbolic representations of material derivatives, so bear with me. The most popular is capital D parentheses over capital DT, although d by dt may also be used. The quantity being differentiated goes inside the parentheses. Both representations are shorthand for capital D over dt. I'll just refer to it as the material derivative now on, so yeah. The material derivative is equal to the partial derivative with respect to t plus v times the partial derivative with respect to x. Note that the last derivative is with respect to x, not capital X. This makes the equation ideal for Eulerian-based applications such as fluid mechanics. It is arrived at by applying the chain rule to Eulerian quantities that are dependent on time and position. For example, the material derivative of temperature, capital T, is the derivative with respect to T of the temperature, which itself is a function of t, x, y, and z, is equal to the partial derivative of capital T with respect to t, plus applying the chain rule. Yeah, I'm not going to read all this out because that would take an eternity, but anyway. This simplifies to the partial derivative of capital T with respect to t, plus x component of the velocity, times the partial derivative of t with respect to x, plus the velocity in the y direction, or the y component of the velocity, times the partial derivative of t with respect to y, and same for the z component. And this is simply equal to the partial derivative of capital T with respect to t plus v dotted with the gradient of t. And this funny symbol is actually called the nabla symbol, or del. And this is equal to the material derivative. This can also be written in tensor notation as the material derivative is equal to t, and then you put a comma and then t, plus vi times capital T, and then a comma again and I. A second example, the material derivative of velocity gives acceleration. So as we all know, acceleration is the time derivative of velocity. So it follows that, as in the temperature case, this is simply equal to all that, which simplifies to this, and again this is equal to the material derivative. And this can also be written in tensor notation, exactly as before. And since velocity have different components, we're actually going to introduce a free index before the comma. So note that I is a free index here. So this above equation for the material derivative of velocity is actually three equations. Representing the three different components, as I just said. So here are the equations for all the components. I'm not going to say them. Then a material derivative example. So my example involves a ball being thrown straight up in the air, and the usual description of its position, y, at any time t, is y equals to capital Y plus the initial velocity times t minus 1/2 gt squared, where y is the initial position. And its velocity is the derivative with respect to t of the position, so it's simply equal to the initial velocity minus gt. And its acceleration is the time derivative of the velocity, and that's minus g, as expected. It's not surprisingly at all. Its acceleration is constant and equal to the acceleration of gravity. And this was easy because the position at any instant is an explicit function of time and its initial position y. But what if instead of position as a function of time, the velocity field was given as a function of position? This is typical of fluid flows, and the velocity field could then be written as Vy, yes, I'm assuming I'm throwing it straight up, is equal to plus minus the square root of Vo, or the initial velocity squared, minus 2g times the parentheses y minus the initial y, where the positive root applies to the ball rising and the negative one represents it falling. It is not readily apparent at all in this case that the velocity equation as a function of position actually represents a constant acceleration equal to gravity, but it does. To see this, apply the material derivative. So first note that this problem is simply 1D, so things simplifies. The material derivative with respect to t of Vy is equal to the partial derivative of Vy with respect to t plus Vy times the partial derivative of Vy with respect to y. And the partial derivative of Vy with respect to t is 0 because the velocity, as described here, is not transient. It does not change with time at any given location. Vy is given above, and the partial derivative of Vy with respect to y is minus plus or plus minus g over the square root of the initial velocity squared minus 2g parentheses y minus the initial y. And multiplying Vy, the partial derivative of Vy with respect to y, out gives it's equal to plus minus the square root of the initial velocity squared minus 2g times y minus yo times big parentheses plus minus g over the exact same thing, so this is simply equal to minus g, as expected again, even though it was quite a bit harder. This indeed gives the exact same constant acceleration of gravity as before, so clearly the material derivative works. And yeah, thank you for watching, have a nice day.